Alright, so check this out. Basically, what I'm going to do with you today is I'm going to help you with your lab, the one that's coming up. Or the one that I assigned this past Tuesday. I think it's due next week sometime. And anyway, we're going to build this lab straight from scratch. And basically, I'm going to go through the steps that you need to take in order to go through this. And then what we'll do is we'll talk about the different things that you might want to include. So the first thing you need to do is record a video. I made a video. Actually, I didn't make this video. I did one of my own later at some other time. But this dude drops a balloon. That's it. Dude drops a balloon, and it falls. It has some air resistance, and my computer froze. Did my computer freeze? What happened? All right. So I think that they put a little mass on the balloon or in the balloon or a battery or something, so it falls a little bit faster. But for the most part, we're looking at this curved motion. Do you guys agree? All right, and I'm not gonna go into how I tracked it. I mean, that's pretty basic from the last lab. You guys can do that. But let's see. I did a meter stick over here. I set my coordinate system so it kind of goes along linear motion. I'm really only interested in the y direction, so I went into my table and I just told it I want y only. And then I copy and pasted this data into Excel, and here it is right here. Cool? If I were to graph that sucker, I would graph it at, that's what it would look like. So it almost kind of looks like a parabola. Let me fix up this thing a little bit more. What I like to do is I like to make those data labels a little bit smaller. I go to marker options, built in. I like using the X's, and I like making them small X's. That's just a personal thing. Maybe a little bit bigger just because they're hard to see now. Let's see. Marker options, make it a little bigger. There we go. There's my X's. Now, check this out. Is this a parabola? Yes, no? What do you guys think? Yes, it's a parabola? No, it's not a parabola? Alright, it looks like a parabola, and actually let me tell you that it's close to a parabola. It's not exactly a parabola, and here's the reason why. It's because with a balloon there's lots of air resistance. So what I'm going to do is I'm going to show you how to do a parabolic approximation in Python, and then after that I'm going to show you how to account for a air resistance. And if I were to show you the straight up math, like if I were to show you know how last week or earlier this week I showed you the math equations of the physics, you know, the delta x equals v naught t plus 1 half at squared and all that kind of stuff. If I were to show you that with, yeah, that thing's a little frustrating. I'll tell you what, I'm going to turn off your audio because I feel like it's. Hello, is that better? You got to chat it to me now, though. Alright, I'm sorry. I think it was EOCAP, but I think your audio was a little funky. Tiger, how are you talking to me now if I muted you?
I can unmute the mic.
Oh, you unmute the mic to talk. Alright, that's fine. I'll just pull up the chat. You guys can chat it up while we're doing it. Don't worry about it, EOCAPA. Don't worry about it at all. Anyway, here, let me try to show you this. Basically, you guys pretty much know how to do all of this stuff. And all I'm saying here is that the projectile motion over here, or not the projectile, but the linear motion that we're talking about, this 1D motion is talking about acceleration. But the problem is it's not just acceleration that we're dealing with, because we're also dealing with air resistance in this particular video, because we're talking about a balloon. And balloons have lots of air resistance because they're so light. Now, if I were to show you the actual straight up equations using air resistance, that would mess you up. I'm actually doing the physics of air resistance right now. In fact, one of my homework problems that I had in Physics 600 was using air resistance, and so that's the kind of math that you would need in order to do the equations. However, if you want to model it using the computer, It's not bad. It's not bad at all. And I'll show you how to do that today. So what we're going to do today is we're going to model parabolic motion, and then we're going to try to make our curve fit even better by adding in air resistance in our Python programming. So basically we want to have Python spit out something that looks like that. And we're going to play with it. And you know what, to be honest with you, I didn't do this whole thing beforehand. So I didn't. I'm sorry. I mean, we're just gonna have to see what we got. Anyway, I'm starting off with the most basic lab 1 start, and we'll see. All right, I'm gonna have it plot that for me and see what we got. Sorry, computer's taking a little bit of time. Come on, computer, figure it out. There we go. Where's my plot? Computer's running a little slow, I guess, with all these programs running. There we go. Alright, this is the basic one that we started off with. First of all, I don't want to start off at -1. I want x to start off at 0. In fact, I pretty much want to just keep x at 0. I want y to start off. Where do I want y to start off? To do that, I'm going to check out my data set. And it looks like at time 0, I have it set to be 2.038. So that's what I'm going to tell Python to use. 2.038. Are we cool with that? Alright. Now, what I'm going to do is, I'm also not going to have it go with a velocity going to the right. I'm going to have a velocity going down. So I want it to be 0, and I want it to be -1. I don't know, I'm just trying to make my graph look a little bit better. Wait a second, what happened? Why is this ball not going this way? And the thing is because when I coded it, I did something funky. This loop right here, my main loop, I need to change this, because right now it's saying set the velocity equal to the vector 0.01, but that's not what I want. I want my velocity vector to be the ball velocity. That way, if I change something up here, it gets changed in the bottom. So it's ball.vel times delta t. And in this case, I'm making delta t 0.0130th of a second. There we go. That looks nice. What do you guys think? Kepa's asking 1/30th of a second. Alright, I'll tell you why. 1/30th of a second is 0.03333. The difference in time between each of these is 0.03333. And the reason why is because my video is running at what we call 30 FPS, 30 frames per second. That means every time every frame is 1/30th of a second. And if I get 30 of these, see, from 2 to, well, almost 30 of these, I'll have just about 1 second worth of data. Does that make sense, Kepa? So this video apparently lasted, it's 30 frames long, but it lasted only 1 second. We cool? And that's why I did 1/30th of a second. Alright. Let's go back to this guy, lab 1 start. Alright, I'll tell you what, why don't I have it spit out this data for me, and then we'll try matching up this graph. Alright, there we go. Delete those lines. Delete this line right here. And delete, not delete the line, but delete the comment type. What is that? Oh, you're right. You're absolutely right. Let's try graphing that. You're right. Yeah, graph is x equals 0. You're right. I've been telling it to plot the ball's x position, but the x position is not what I'm interested in. I need the y position, and I also need it to do that over here. So I changed that over here, and then this would be position. But instead of calling it position, I'm going to call it height. Alright, if I F5 that, there's my position, there's my graph, bada bing, bada boom, we're good. So therefore, I'm going to have it spit out. Actually, and you know what? I only want it to run for 0.093. I only want it to run this long, so I'm going to have to stop it earlier. Click on this, click on this. I don't want to run it for full 2 seconds. I want to run it for that many seconds. Let's. Okay, yeah. All right, fine. Let's pull this data out and we'll see what we got. Something's not right. It should land over there, right? It should hit the bottom of the, hit 0. So we need to speed this ball up. Let's not make it -1. Let's make it -2. Let's see what happens. I just want to get close. Yeah, that's about right. All right, good. Let's pull that data out. Let's see, where did I put that? It was under desktop. I think I have a new folder in there somewhere. New folder there. And then here's where my Python files got spit out. And I take this. There we go. And I'll grab him. And I'll copy and paste him into book 1. By the way, I'll close this guy out. Alright, now I'll copy and paste this guy right here. That looks perfect. Awesome. Alright, we'll delete that. We'll delete this whole thing. And we'll compare these two graphs right next to each other. Sound good? Insert. Scatter plot. That. Alright.
Python data, though.
Red's my Python data, blue is my actual data. That doesn't look good at all. Remember, I made, basically what I showed you on Python is how to do linear motion. I just showed you linear motion. We don't want linear motion. We want changing acceleration motion. Alright? So, what you're going to need to do is, alright, at the very top, what is the initial velocity of the balloon? It's 0, so we need a 0, 0, 0, right? And then here's where our velocity will come in. See this velocity? The velocity changes. And how does it change? Well, it changes as a function of gravity. So I need to put in a few things into here. And, oh, excuse me, sorry. Okay. Alright, here we go. Here's what I'm going to do. Tell me if you guys are confused by this. I hope you're not. I'm going to call something, let's see. How did I do this earlier? I forgot. Alright, here's what I got. I'm going to say that I'm going to add in gravity. Got it? Now, gravity is equal to 9.81. And this is measured in meters per second squared. We cool with that? Actually, I'm going to make it negative 9.81. Where's the 9.81 from? That is the definition of gravity in meters per second squared. That's pretty much, you're going to memorize that number. I'm just going to look up gravity. You're going to memorize that number because if they ever tell you what is gravity, then you say, oh, it's 9.81. Actually, if you want to be very technical, gravity changes from depending on its location, and so gravity, the value of gravity for Hawaii, I have it written down somewhere. One second, let me find it. Is, let's see. Oh, here. Is actually 9.78449. You can go look that up. It's interesting how gravity is different depending on. It's actually gravity Gravity is the value of gravity depends on where you are in terms of altitude. So that thing is actually, it does change depending on where you are in terms of altitude. But basically, the most common one is 9.81. So let's just stick with that, if that's all right. Because to be honest with you, I have no idea whether or not this video is made in Hawaii. Actually, I know for a fact that it's not made in Hawaii. So that's gravity. All right. But what I also defined was I also defined a unit vector, j hat. And I need to tell Python that I'm talking about a y direction vector. So I'm talking about a vector that goes 0, 1, 0. Are we cool with that? And this is really just a unit vector to signify the y direction. Remember, these comments that I'm putting a dollar sign in front of, or a number sign in front of, is really just to kind of show you what I'm doing. The computer doesn't read it at all. All right, and so I want the vector, the gravity, to equal to, or I want the weight to be equal to gravity times j hat. Right, so this is telling me that I have a gravity vector of magnitude negative 9.81 in the direction of the y direction. Are we cool with that? I just turn, this is a scalar, this is a unit vector. When I multiply the scalar times the unit vector, I get another vector in the direction I want. That's how I approach it.
So how do you do that as a magnitude here?
Well, gravity, the way I have it set up, I just set it up as a number. Gravity is negative 9.81. The reason why, actually, you know what? Technically, I should probably just put regular 9.81, and then I should put my weight is negative gravity times j hat, because, you know, I mean, the weight is the one that's pulling down. We cool?
Okay.
All right. And then what I'm going to do is I'm going to use the force to change my velocity. So it's saying my final velocity is equal to my initial velocity times something. All right. It's times the force, so it's F net divided by ball dot mass times delta t. And I realized I didn't make ball mass. I didn't tell you what the ball's the mass of the ball was. So I better set that up. Ball mass, and I think they gave it to us in the video. 8.6 grams. But I'm dealing with kilograms here, so I want to make it 0.0086 grams, or kilograms. Equals 0.0086. I'll tell you it's in kilograms. Alright, so there's the ball's mass, and by the way, the force that we're talking about is the weight. I think that's all you need. Let's try that. Does this make sense to you guys? Yeah, alright, cool. Let's see if that works. Hopefully it does. And I didn't pre-do this entire lab, and I'm actually recording this whole thing. I'm putting it up on YouTube, so that now you guys can watch and rewatch all you want. Whoa, 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 whoa! That thing went fast and far. What happened? I know what happened. I know what happened exactly. The weight isn't just it isn't just gravity j hat. It's the weight is mass times gravity. So I need to put the ball's mass up here. Does that make sense? Weight is mass times gravity. And so that should help it out a little bit. Let's see what happened. Let's see what we got. There we go. There we go. That's perfect. Well, almost. Okay. Yeah, well, I'll tell you what. Let's try graphing that and see if that's what we want. So if I take that and I pull that data now, that'd be this guy. Sure, I'm going to get some negative numbers, which could be a problem, but that's why we need air resistance in there to kind of offset that. You'll see what I mean. You know what? I'm going to wait, Control Z. I'm going to put that there. All right, delete this thing right here. I'm going to graph all three of those. Scatter plot. Okay, so check this out. This right here, the blue was our actual data that we plotted, okay? The red was if I dropped something and it fell at a constant velocity. That is totally out. The red is a dumb graph, right? We shouldn't even use that data. The green is what I did when I added acceleration, and it's getting closer. Do you guys agree? Like it's kind of off, but it's getting closer. Are we cool with that? Now, yeah, exactly. I mean, just by looking at this, you can totally tell that you need air resistance. Now, to be honest with you, do you always need air resistance? Yes, air resistance makes a difference, but for the most part, and the physics that I'm teaching you, you know, the ones that you have to do by hand, that physics, that's using no air resistance. That's all going to be the green graph style. So obviously, the physics that you're learning, and you're thinking, oh man, what the heck? Why are you teaching us the physics that doesn't perfectly model the blue graph? And the answer is because if I can teach you to think in this way, it will help you to eventually get to here. And I don't think we'll ever be able to get to here in this class, like to be able to get to this, the math of this blue graph, because you need, like I said, you'll need at least this course called Partial Differential Equations in Mathematics, which is like 6th year calculus. Or at least, I mean, it doesn't even go Calc 6. It's basically, it goes Calc 1, 2, 3, and 4, and then after that, you have to take 2 more classes, and then you'll get into partial differential equations. So, but on the computer, we can actually totally model it. In fact, I'm going to show it to you in the next 10 minutes. So you're going to be like, whoa, that's crazy. All right, so are we cool with modeling parabolic motion? Now, I'll tell you what, if we're going to use a balloon, your graph will probably look something more like the blue line. If you're going to jump off a cliff or something like that, or drop a basketball from a height, from a ladder or something like that, it will look actually more like this green line, and then you'll have less to play with. It will be harder to track, but it'll have less to play with. Does that make sense? All right. What I would do is, so for your lab, you don't have to model it exactly. I would say for your lab, model it as close as you can. And if you can get the thing to go closer, the closer you can get, the better. All right. So what I'm going to do is I'm going to add a thing called the drag force. Now, the drag force depends on how fast you're going, and that's actually something that's why it gets kind of funky, is because the size of this force, the size of your weight force is a constant. It's your mass times the gravity times the height, and that's it. But the drag force actually will change depending on how fast you're going. If you're going super fast, then what? Is there a lot of drag, or very little drag? Super fast means lots of drag. Not fast at all. If you're not moving, then there's no drag force pushing back on you. You know what I mean? Like, think about jumping out of a plane. If you jump out of a plane at the very beginning of your jump, your cheeks don't get all flappy, right? But as you fall faster and faster and faster, the more flappy your cheeks will feel, and the more force you'll feel pushing up on you. Does that make sense? In fact, not only does it depend on its velocity on just the, well, anyway, here, we'll do that. All right, so we'll add in a force, and we'll call this the FD. Cool? And this is the drag force. So I'm telling Python I want a new variable called the drag force. And the drag force is equal to some number, I don't know, let's make it B, times the velocity. Actually, I'm going to create this drag force within my loop. So my drag force is some value B times my velocity. We cool? I need a time symbol in there. And which way does it point? Well, my drag force actually points in the positive direction. So I'm just going to make it this FD. So I'm adding my drag force to my force net. And my drag force would depend on what the velocity is. So the reason why I made it within the loop is because the velocity starts off at 0, but as the velocity changes over here, the drag force will change respectively. Because it will get to this, what it will do is it will update the drag force, it will update the force, it will update the velocity, it will update its position, the time, and then it will come back and change all of these things depending on how all of these other variables change. And it will loop around and around and around like that. So I think that that would be good. The only thing I need to do is make sure to specify what B is. And to be honest with you, I don't know what B is. I think that we should say B is equal to, I don't know, 1. And I'm just making this up because I have no idea. Actually, let's make it 0.1. I think that drag forces are around, closer to around there. And the way I'm going to do this drag force is let's F5 that. Let's see what that looks like. Oh, it didn't like. Oh, you know why? Because I need. I had Python test open. There we go. F5. Whoa. Whoa. Well, that sure changed the shape of my graph. That's for sure. A little bit too drastic, though, huh? I'll tell you what. I'm going to play with this until I can get it to be 0.01. How's that? There we go. There we go. And I'll tell you what. I don't know if that worked. So what I'll do is I'll plot it up against my other graph, and I'll see. See, I'm going to just copy and paste that data. One. Okay. Tell you what. Let's do that. And we'll graph all of that. So scatter plot. All right. Okay, this one I don't want. This one I don't want. What did I do? What did I do wrong? Because it looks like it made my graph worse. I'll show you what I mean. I want my this graph to get closer to this red one, but it got further away. The drag force is negative. What is it? Let's try that. The drag force is negative. All right, let's try that. Oh, darn it. I have this thing open again. All right, drag force is negative. There we go. All right, let me try graphing that and see what happens. Open the Python test. Copy and paste that. All right. I want you to look at my old graph. That's my old graph. This light blue line, I'm going to see if I can change it. Doing that help. There we go. There we go. Look, 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 look. This blue line is closer to our red line. Awesome. Alright, so 0.1 doesn't work though. What do you want to do? You want to go make the drag force bigger or smaller? Let's make it 0.2. Well, if we make it 0.1, it's going to look terrible, but if we do 0.2, I wonder if that works better. Oh wait, it's going to tell me it doesn't like me. I keep forgetting that. The reason why I made it so clear that that's a problem is because I keep on messing that up. Alright, in fact, I'm actually going to, it looks like it even got better. I'm going to make it so that it ends right at that yellow dot. And to do that, I'm going to kind of cheat, and I'm going to say, alright, I want you to do a print statement. I want you to tell me the y-st position at that time. And we'll see if we can make it just a little bit bigger. Like, let's say 0.02. You guys want to try 0.03? Basically, all I have to do is look at this shell and see if okay, it's close. It's close to 0. Let's make it 0.028. 0.028. There we go. Let's try that. I'm basically trying to make this number, the second number, as close to 0 as possible. Okay, let's see. How's about 0.029? I'm just messing with this so I can find a B that's close. We're getting good. All right. How's about 0.0299? That's even closer. How's about 0.0295? I'm just, you see what I'm doing? I'm just playing with this until I can get this as close to 0 as possible. That got further. So 299 works. Good. Should I try one more? How's about 0.029876? I don't know. I'm just making up numbers at this point. That's as close as I can get it. All right. Anyway, 0.0298 is my answer. 2987. I don't know. Okay. So I'm going to pull that Python file out. I'm going to map it, and we'll see if I can get it to be exactly the same. Here was my old data when I had it as 0.2. Now I want to do my new one and see what that does. Dude, you gotta admit, these are pretty close. What do you guys think? You guys aren't very talkative. Can it get closer? Yes, actually it can get closer. Because I need to tell you that actually the velocity of the ball is not just, the buoyant force, or not the buoyant force, but the drag force that you feel is not dependent on only the velocity. It's actually dependent on the velocity squared. That's what it's really dependent on. So in order to map that, and I'll show you guys, and what I'll do is I'm just showing you, and I know I'm showing you this fast, and I know that you might not even get all of it. But the reason why I'm showing this to you is because, I mean, I'm making a YouTube video out of this, and then basically you guys can watch this over and over and over until you guys get it. And this is pretty much how you're going to do your lab. Now, what I would do is I would say, okay, I want to do the ball's velocity times the ball's velocity. Now, what that does is it's going to show me an error. It can't do a vector times a vector. So I'm going to have to tell it I want a scalar times a scalar. Magnitude. That's the scalar part of the velocity. And then I'll just do that one again, mag. That's the command to say, all I want is the ball's velocity, but just the scalar part. I wonder if that will work. I think what I have to do is maybe do the normal of this. Let's try that. There we go. This right here. So just remember these commands, and I'll explain to you after why I have those commands. But if you want to do the velocity squared, you'd have to do this, and then you'd have to do this. We cool? And I need to change my B, because even though it might look closer, my B is the B that I had set, this, whatever constant, is set for what if the velocity were only just velocity dependent instead of velocity squared dependent. So let me try making 2, 5, and I'm just playing around with this to see if it works. I want to get that second number close to 0. Okay, wait. 2, 5 is bigger. How's about 1, 5? And then I play my game again and just get it so that it's set to 0. Okay, we're good. We're close. Okay. How's about 0.1? Actually, you know what? Where exactly does the tracker end? The tracker ends at 0.133. So I want it to be 0.133. How's about 1.7? Let's try that. I want this number, this second number, to be 0.133. Okay, right. How's about 1.65? I'm gonna try that. There we go. 1.6. I'm just making it a little smaller. There we go. All right. Now watch this. If I were to plot this data up against my other one. All right. I'm going to plot it one more time, and I'm going to show you. Hopefully, they'll be pretty, almost like on top of each other. All right. And then this data right here is nothing, and this data right here. All right, so let's try this. Delete. And I'm going to go like this. I'm going to graph that, and let me go over what I did. There we go. There we go. This is beautiful. Okay. Let me zoom in. Move chart. New sheet. All right. So here's what we got. Blue data is what tracker threw out. Got it? Blue data is what tracker threw out. Red data is what Newton throws out. This is not considering any air resistance. It's not a very good graph. I deleted it. Green data is using only velocity. And X data is using velocity squared. So what you can see is it almost looks like towards the beginning of the motion, the velocity, you know what I mean, just when it's dependent on velocity, it almost looks like it's better. And then towards the end of the motion, it looks like, more straight, and the velocity squared is a better match. So the answer is actually the velocity squared is your better match. And so that's what you can do. That's how you do air resistance. You just add it in as a force. And the reason why we can't deal with velocity in or deal with air resistance in our regular physics equations that we're talking to you about is because the air resistance, that force, changes depending on how fast you're moving. You can deal with Python easily because Python will just change those numbers. Does this make sense to you? I need a response from everyone, just so that I know that you guys are you know, I mean, you guys understand kind of what's going on. And then just to show you guys,
Yeah.
I did my other one, and I'll give you this file as your starter file because I think this one's cool. This is, whoa, what happened to? Oh, you know what? I have the Python test thing open. I got to get used to that. All right, let me show you what the Python file I wrote for when I did it later. I did it like this, where it graphs it for you, and then you actually get your XY coordinates, and it tells you where it lands and all that kind of stuff, and it looks a little bit nicer. If you want, I can give you that as the starter code, so you guys can look at it like that. But it looks pretty cool, huh? And so this was one that I did earlier, and I had my daughter drop coffee filters, like 10 coffee filters or 5 coffee filters. That's what it was. And the graph that I had it spit out. In fact, if you look over here, you can see signs of what I was doing. This is the drag force that I was teaching you about. This is actually the drag force. The same drag force is just, instead of writing just a B, I wrote 1/2 C rho A. And that's actually what the drag force is actually dependent on. But for now, I'm just teaching it with a B. And B can be anything. It's just a number that you play with until you get the thing to match up perfectly. So you can kind of see what I've been doing over here. I also added a separate force called the buoyancy force. And that has to do with something else. And I'm not, I mean, I can show you that later, but I'm not going to teach it to you now. Anyway, before you go, all I'm asking is, do you have any questions on this stuff? And I'll give you this link to go to YouTube so you guys can process this and kind of, you know, get your head around it. But pretty much that's it. We cool? Any questions? No questions whatsoever. All right. I'll talk to you later then.